Welcome to Derivatives Problem Examples Part 1. In the previous video, we looked at the slope-intercept form and we derived or looked at the derivative compared to the slope, the m in the formula. And we found that the derivative, the end result, dy dx, is equivalent to the slope at an instantaneous point on a line or a curve. And so in the previous video also we talked about how to do a derivative. If we've got a y equals axn, then the dy dx is equal to anx raised to the n minus 1 power. And we define what y is y, x is x, a is the number in front of the x, and n is the exponent of the x. And we also said, hey, it's just easier to do a few of the examples. So we just need to work through some problems, and that's what we're going to do right now. All right, problem number 1, which was the exact question that we went through in the previous video. But we're going to go through it again just as a review. So if we've got y equals 3x plus 4, remember that's the same as y equals 3x raised to the 1 power plus 4x to the 0. Anything raised to the 0 power is equal to 1, so it does not change that statement any to say 4x raised to the 0 power, but it does help us apply the derivative model so that we can take the derivative of that. And so we find once we take the derivative, we've got dy dx is equal to 3 times the n, which is the 1, x raised to the n minus 1, which the n was 1, plus 4 times 0. And once we see that 0, that n for the 4x, that switches to 0, and then the next part becomes na, not applicable. And we can then simplify that out as 3x raised to the 0 power plus 0, and then solve for a dy dx equals 3. And I've got the Desmos graph of y equals 3x plus 4 here. And just like before, if we calculated the slope at any point on that line, we would see that the slope is in fact equal to the derivative dy dx of 3. All right, next question. So if y is equal to 3x squared, I've got that graphed in Desmos here, y equals 3x squared, and we can see it's a parabola facing up. And if we take the derivative of that, we end up with 3 times the n, which is 3 times 2, the n being the exponent of the x, times x raised to the n minus 1 power. And that leaves us with a 6x. So we can see now that the slope is dependent on where we're at on the x-axis, the slope of the curve, because we're now curvy. So let's dig in a little bit more with that dy dx equaling 6x. So the idea that because this is a curve, the slope is dependent on the x, we can look at it and say, okay, well, at 0, if x is equal to 0, then it really looks on the graph like that is where the slope should equal 0. And if we put that back into our derivative formula, 6 times 0 is 0. There's 0 slope at when x is equal to 0. And then if we march that out and say 0.6, well, we can see out here it's like a little less of a slope, and then as we further get out on x, it's getting steeper and steeper. And as we increase x, we can see a steeper slope to the positive with a positive x, and then if we went and put a negative x in, we can also see a steeper slope, but it's going to be sloping down left to right, so we're getting a negative slope. All right, so question number 3, y equals x squared minus 2x. Now we've got two variables in here, and when we graph that in Desmos, we see that it's similar parabola as before, but it looks like it's offset. And it looks like where the slope is 0 on this parabola would be x equals 1. So if we take the derivative of the y equals x squared minus 2x, we get 2, because imagine there's a 1 in front of that x. So 1 times the exponent n, which is 2, so we get 2, x raised to the power of n minus 1, which is 2 minus 1, minus the next term in that equation, minus 2 times x's would be raised to the 1, so you've got a minus 2, and then times x to the n minus 1 would be 1 minus 1. So we end up with a derivative of 2x minus 2. And we can see in that equation, if x was 1, right, you get dy dx equals 2 minus 2, which would give you the slope of 0, which is exactly what this graph is showing us. All right, question number 4. Y equals 1 divided by x. Okay, so this one, in order to help us use our format for the derivative, it's easier to me if you move the x up into the numerator so that you get it all looking like this second line. So y, if you do that, then you end up with y equals 1x raised to the negative 1 power. So remember, when you cross a line, you change the sign. So x is raised to the 1 power in the denominator, but when I bring it into the numerator, we flip the sign. Cross the line, change the sign. And so now to take the derivative of that, you can see we've got minus 1. So 1 times a minus 1 gives me the minus 1. X raised to the n minus 1. Well, the n is the minus 1 minus another 1. So that gives us the negative 1x raised to the negative 2 power. Now, that is technically correct right there, that derivative with raised to the negative 2, but it's not, I guess it's not aesthetically pleasing. So to make it a little prettier, we're going to move it back to the denominator, and we get that dy dx equals negative 1 over x squared. And when we look at the graph, we can see that as x increases, and we look at our dy dx, or derivative, as x increases, right, technically all the way to infinity, we get a smaller and smaller slope, right? Anything divided by something that's getting exponentially bigger all the way to infinity would start to get small, exponentially small. So you can see that on the graph, as we move x up, we get a smaller slope. Now, you can also see that on both sides, we've got the same answer on both sides. That's because of the x squared. So technically, we could have a negative times a negative, or a positive times a positive to get that, then that gives us the left and the right on the graph. Same thing for the vertical. As we become closer to 0 in the denominator, the answer becomes infinitely large. So as x gets really, really small, approaching 0, we get an infinitely large slope. And we can see that in the y-axis there at 0, where it's looking like it's shooting off the charts steep. Now again, that's positive and negative because of that x squared in the denominator. So this one, it's going to start out similar to the other one, but we're going to have to do an extra step, kind of a different step in this, and you just need to see it probably just once or twice before you kind of catch on what's going on here. So we're going to do the same thing. We're going to move the denominator up into the numerator for the y, and that gives us the y equals 2 times the quantity x minus 3 raised to the negative 1 power. But now when we take the derivative of it, we've kind of got to do a two-parter here. So we're going to treat the whole parenthesis part as though it's almost like its own x, and we're going to leave it alone. And so we're going to start out, we're going to take the 2 here times the negative 1, the n of the negative 1. And that gives us that negative 2 out there in front for the first part of the derivative. And then we're going to leave that inside part alone. So we've got x minus 3. Almost treat that like it's its own x term, raised to the n minus 1 power, which is minus 1 minus 1. And then what we do, the next step is now take the derivative of the single x on the inside. Okay, so that's x raised to the 1 power, so we've got x raised to the 1 minus 1, and that's that last little part on that first line of the derivative. And now we can just go ahead and start simplifying. Our minus 2 drops down. Our x to the minus 3 quantity is now raised to the minus 2 power, and that last little bit is x raised to the 0, which that then becomes just 1. Anything raised to the 0 is 1, which leaves us with, all the way down here at the bottom, we end up with a negative 2 divided by x minus 3, that quantity squared. And we can see now, what's interesting about this now, it's kind of got the same pattern as the previous problem for the graph, but you see that it's offset by an x of 3. Well, you can see now the denominator here in this question, as x approaches 3, positive 3, that bottom quantity is becoming 0, which means now as we approach 0 in that denominator, our slope is getting exponentially steep. And it's the same deal because we've got the squared. We could have a negative times a negative or a positive times a positive, and that's giving us both sides of the axis.